Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, restore IP addresses. So what this problem basically says is we get a valid IP address that consists, so basically it defines a valid IP address as 4 integers that are separated by single dots. So something like this one here, right? 4 integers, this one, and this one, this one, and this one, right? And they are separated by single dots, 4 in total, right? 3 in total. And each of these integers needs to be between 0 and 255 inclusive, including 255. And you cannot have leading zeros. So you can't have 0, 1 as a dot something, right? And maybe something here. But you can have just 0 alone, because for an IP, 0.0 4 times is actually a valid IP address. Okay. Yeah. So for example, here they give us just a couple of valid IP addresses. So this one is valid. A single 0 is valid. This one is valid. All of them are within the desired range, which is 0 to 255. But these are not valid. So for example, this one is not valid because there is a leading 0 here. This one is not valid because... why is this one not valid? 192. Yeah, because 312 is bigger than 255. And this one because there is this character that shouldn't be there, right? So that's the idea. Now, what do they want us to do? We get a string, just a long string like this one. And we want to find all the valid IP addresses that we can get from this string. And this is because we can get different ones. So for example, from this string, we can take 255, that's a valid thing, as the first portion, and then take the second one, and then take the third as we can take only 2, and then for the last one, take 3. So that's the first one here. The second example is take 3 here, 3 here, 3 here, so that's 3 ones, and then take 3 5, and so that's this one, and it's valid. And those are the only ones that are valid. You might think, okay, maybe let's take 25, but then if you take 25, you will end up with something that starts with 5, like 525. That's not valid, right? You could decide to take, okay, 25 and 52, but then what about for the third number? If you take 55, that's valid, but then you have more numbers that then can fit in with just one dot, right? So actually the only valid ones, you can try different variations, but the only valid ones are these two. And with 4 zeros, it's just 0.0.0, right? Now, one thing here one big hint here is with the constraint. So we have s, the length of s is limited by 20. So this tells us basically that an exponential solution should work fine. So if you have 2 to the power of to the power maybe of n, or you have even 3 to the power of n, these all should fit fine, right? And so immediately when you see something like this, then think about doing backtracking or some sort of recursion, because it should largely pass, right? Okay, so now let's try to solve it and see what we come up with. Okay, so how do we solve it? So we said that when we see a constraint like 20, we should be able to do some recursive function like using backtracking easily, right? So how do we apply to this? I'm going to take a slightly different approach than probably most of the other solutions, which use a dot and basically backtrack based on that dot. I'm going to do it differently, where I'm going to backtrack basically and do choices based on the number, right? So what is the first observation here we can take? So the first observation is that, well, for each number, you have only 2 possibilities. Either you add it to the part before the dot that you will need to add, right? So we have 4 parts, right? So for an IP address, we would have something like 25, 11, maybe 137 or something like that. So we'd have X, Y, Z, W, right? So we'd have only 4 parts. So if we think of it as parts, then for each number, we only have 2 choices, either include it in the current part or start a new part with it, right? So for example here, what are the choices we have? Well, for this 2, we can, the 2 is the first, so we'd have to start a new one. So we start a new one with just 2. Now what about this 5? Well, this 5, we have only 2 choices. We can either decide to include it in this. So we have 2 choices for this 5. We can either include it in this portion and make it and make this part here be 2, 5, or we can decide, okay, no, actually, let's start a new one with just that 5. So if we start a new one with just that 5, that means we will add a dot and we will have 2 and then dot 5, right? And if you can choose in your backtracking to just have these as a list and then join them with the dot later. And so here, what this would be is, let's try it actually. So let's start with our I position at the first element. Sorry. So each element can be, so let's say we would have 4 parts, right? X, Y, Z, and W, right? And so here, for 2, we would have to start a new one because we had nothing. So this would mean here that we would have, so our state of parts is going to be the first one has 2, but the other ones we haven't added anything. So the other ones are empty, right? And then we continue this decision tree here. And so we go to 5. So our I moves to 5. Well, 5, only 2 choices, either included as part of the first portion or start a new one. So we would either have to do something like included, which would be like this in the first part, or start a new one, which would be leave the first one as 2 and then start a new one with 5, and then the rest are empty like this. Okay, and similarly, with this one here, we'd have, for this I, we'd have 2 choices, either included, so we have 2, 5, 5, right? Or start a new one, which means we'd have 2, 5, a new one with 5, right? And you get the idea. And same thing here, processing here for this 5, either included, which means have 2 included in the previous one, right? And have 5, 5, like this. Or exclude, or start a new part with it, which means you would have 2, and then 5, and then another 5, and then like this, right? And you get the idea. You can continue the decision tree until the end, right? And so with this, at the end, we would have, let's say, for example, we continue with this one, and we ended up with this. So we'll continue, and then we'll end up starting a new, we would have to start, when we reach a part reaches 3, we'd have to start, because remember, the limit is 255, right? And so here we start a new one after this 5 here, and so that's 2, and let's say this last one is just 2, 5, 5, and then 1, 1, and then 3, 7. Okay. Then with this one, we can just, at the end, to get the IP, we can just concatenate each one of them. So this one is going to be 55.11.37. The other option is, instead of using a list here, we can just use strings, and that would be basically means we will have this be like 255, 11, 37, and then at the end we can just use join to get 255.255.11.37. And this is actually, I prefer this approach than having a list, just because it's easier to visualize. Okay. Now, so that's just the vanilla doing the backtracking. Here there are a couple of conditions that the problem tells us to take care of, and so we'd have to take care of them while doing our backtracking. Those conditions, there are 2 of them, right? So the first one is that the value needs to be, for each portion of the IP address, needs to be between 0 and 255 equal, right? And the other thing is that no leading zeros. Okay, you can have 0 alone, but you can't have 0, 1, for example. So this one is not valid, but this one is valid, okay? And so we just have to take care of those two. To take care of this one, basically, when we are doing the branching, let's just do not pick the element if it will make the number bigger than 5. So if adding the element to a portion, or let's call it a part in some position, if adding the number which is s at I, if that will make the number bigger than 255, then just don't call the recursive function with that number, right? Pretty straightforward. And similarly, if when we add this, we get a string that starts with 0 and the length is bigger than 1, which means it's not this case, then also do not take that choice, right? And so that's how we can apply these two conditions. Okay, so now that we know how we'll handle it, the only thing left to do is to think about, okay, how would we implement it? But the first thing we will need is what would be the state of the function? What would be the parameters we need to pass to our function? Well, we need our helper function. We, of course, need the index. So you can see what I used here. I needed to move this I every time. Okay, so we definitely need I. And that will also help us to know when we are at the end of the string when we reach I here, right? The other thing we need to know at which position of the parts we are at, right? Because each time, let's say when I'm at this I here, well, I need to know whether I'm in the first part or in the second part. In this choice, I'm in the first part, and so I know I have two options, either to try to add to this part or start a new one, which is going to be the previous position plus 1. If it's this choice here, then I need to know that the previous position was 1, and so either I add to position 1 or I start position 2. Here the previous position was 0, so I either start a new one at 1 or add to the previous position 0. So we need the position in the parts, right? Remember, I'm calling these things here parts, that the parts of the IP address that will end up concatenating, right? And the other thing we need is the actual list. So the actual list, this one here, right? The actual list. And this list is just a set of parts of the IP address. So let's just call it either IP or parts, whichever you want, right? I will call it IP. Okay. Okay, so that's our definition of our function. Now, what are the different calls we want? So we have two choices, right? We can either two choices, right? And that's usually backtracking is just a set of choices. So either put the current character, which is s of I, in the current part. So in the current part, okay, or start a new part, okay? Now, what's the condition for starting a new part? Well, remember, we can't have an empty string. You can't have an IP like this with just an empty string, maybe 1 and then 2 dots and then 224 or something like this. You can't have 2 dots like this. So we can't have empty here. And so we can't start a new part unless the part before it is not empty. So here it's only allowed if current part, the length of current part is bigger or equal to 1, right? And here also adding a new character to the current part is only allowed if the current part is smaller than the length of the current part is smaller than 3, because otherwise, let's say 250, we already have 255. You can't add 2 here, right? Because that will be bigger than 255. Even if you had just ones, you can't add another one because that would be bigger than 255, the limit. Okay? And so here we want to check if we want to check for this condition, and then we want to also check for leading. So here check for length plus check for not leading zeros. So we want to not have leading zeros. But then after that we can just call helper again on the next index of S. And since here we are staying in the current part, right? So the first choice is adding SI to the current part. We can keep the same position and just move parts. But the other thing is we need to change parts at the position to include this SI. And so it's just going to be like this. But because this is backtracking, we will just need to save whatever value was in this so that we can add it at the end. I will show you that in the detailed implementation. But the main idea to think about is how to change it and how to call your function. Now for starting a new part, of course we need to check that the length is bigger or equal to 1 for the part at position. And we also want to check that we are not at the end of the IP address, right? So let's say we already did 1.1.1, right? .1, and we are at this here. We shouldn't start a new one in this case, right? Because the IP address is done, right? And so here we want to also check IP, basically check the length. The part position is smaller than 3. That means we haven't filled all the IP parts yet, right? And so here we can just call our helper function again on I+1 to go to the next character. But we are starting a new part, so we want to call position +1. Okay, and we pass our parts here. But remember, we also want to change the new part, which is going to be after the previous part. So position +1 needs to start with the new character because we are starting a new part with it. Okay, and then at the end, after calling our functions, we want to revert our change. So parts at position +1 is going to be equal to empty string, right? Don't worry, I will write the implementation in more details, but just to give you the idea, backtracking, do a set of choices, and then if you have some constraint, make sure to put them before your helper function call, like we are doing here, and then call your helper function, okay? But also make sure that if you do some modification for that helper function call, make sure to cancel it at the end so that the next call is not impacted, right? And then of course we will need to do our base case here, but I'll show you that in the detailed implementation. Yeah, so that's pretty much the idea here is we would have only 2 choices for each number, whether to include it in the current part or include it in a new part. And then we'll just apply our conditions. Yeah, so let's implement this and make sure it passes test cases. Okay, so let's implement this change. So first we need to define our helper function, right? Let's actually just call it, helper, like we did with the overview. And so we need I, and we need the position, and we need the parts. So we need to initially call it with starting position, which is 0. Starting position is 0. And the part we said we just need 4 strings, right? For the 4 parts of the IP. And here, if I is equal to n, that's our base case, right? Because that means we did the entire string. And so we need n to be the length of the string s. And we need something to store the result, and that's what we are going to return at the end. But remember, we store the result as here as a list of strings, and so we will need to sort of join them, right? So here let's call map lambda x, and then just join with the dot, right? This is going to join for self.res. And of course this is going to be a list. And then here, the important part here is the base case. So if we have and we reach at the end, we want to add to the list of the result, we want to add the parts. Okay, so we have this base case. Now we need to do our use cases. So remember, the first one is basically means add si to the current part, right? And so for that one to do that one, well, what do we need to do? We need to add to the parts in position, we need to add s of I, and then call the same position because we are still in the same part, and then this will pass as it is. Now with the backtracking, we need to restore the previous value that parts at this position was in. So to do that, let's just store it in a temp variable so that at the end here, we just restore it, okay? This is going to be temp, right? Okay, so this is add to the current part, so this is our first choice. Now our second choice is to add s of I to a new part, okay? And so what this would mean here is we will need to call our helper function on I+1, of course, because we are going to the next character, but we are going to the next part. But since we are going to the next part, we want the next part to have s of I. That's what we want here. So we want parts for position at +1. So this is the new part is at the next position. We wanted to remember this is the first letter in the new part, so we needed to be assigned to it si, right? And now here we want to restore it back to the previous state it was in, and that's just an empty string, right? Okay, so now we have our two backtracking choices and functions. The only thing left to do is to do the constraint that we have. So the first constraint is that we are only allowed to add to the current part if it's not full yet. And not full means basically we have the length is less than 3, because if it's equal to 3, we shouldn't add to it. And so here we want to check if the length, right, of the current part is smaller than 3, only then that we want to add. So we want to do first this. Okay, so that's the first condition. The second condition is we needed to not have leading zeros. Okay, so when do we have a leading zeros? So if part's position, so we don't want part at this position, right, to start with 0. Okay, if it starts with 0, that means, and this is the current part, that means we already added a value, and there is a new value that we are adding after it, but it starts with 0. So if this condition is true, that means we will have a leading zeros if we add this si to the current part, and so we don't want to do that, right? Okay, so that's for the current position. Now for the other thing is that we don't want, for example, 2, 5, 6, right? And so we also want to check against that, okay? And so how do we check against it? We can check here if the parts in position after adding this si, only if it's smaller or equal to 255 that we want to proceed. And we want to convert this to an int, of course, so that we can compare the two integers. So only in that case that we do here, okay? Now to the conditions for this case here, what are the conditions? Well, we need at least one. To start a new one, we need the previous one to have at least another value. This is so that we don't end up with something like 1 dot and then another dot, because this is empty. So we want to check that the length of the previous part, or the current part, let's call it, is at least bigger or equal to 1. And we want our position to be smaller than 3. Why? Because if it's equal to 3, that means we already have something like this, right? And so it doesn't make sense to add another one, because then we will violate the IP. And so we want to avoid that, and so that's what we do here. And that's pretty much it, right? I know it took a lot of the conditions here, these two conditions, but I really wanted to solve this with the two choices, because I find with backtracking, you need to first get used to these two choices way of doing things, and then you can graduate to more complex things. Okay, so let's run this, just make sure it passes. Now looks like we have a problem here, so let's first just return our result that we add to it, and let's see what we have. So looks like we have empty, and that's because this is a common problem, by the way, with backtracking, is when we don't copy the list, it ends up getting changed in the next call, right? So let's just avoid that. Okay, so now it looks good. You can see we have our strings, our parts here as strings. So now we just need to join them. And so we need to map lambda of x. And then we want to join with a dot for each x. And we want to apply that to these selves. And then we want to return list. Okay, so it looks like these two test cases are good, except this one. And that's because of this last, that's specifically because of this case. So let's see how we can avoid it. So why does this case happen? This case happens if the last part is empty. Okay, so we just need to check here if we want to add only if the last part is not empty. So we can either do a length of this bigger than 0, the last part, then we add. Or in Python, it's more idiomatic to just do it like this. Okay, so let's run this. That should work. Let's submit, and that works as it should. Okay, yeah, so that's pretty much it. It's actually pretty simple. It's just you need to make sure that we respect the conditions of smaller or equal to 255 and no leading zeros. But this adding the number to the current part or the new part should be straightforward, hopefully. Yeah, so that's pretty much it for this problem. Please like and subscribe and consider supporting my channel on Patreon. Thank you, and see you on the next one.